At spring equinox point, both right ascension and declination of our sun are zero. In summer, sun reaches highest point and day length becomes truly maximal for us. In winter, declination reaches minimum and the celestial body rises in the cold southeast. Seasonal change happens due to the axial tilt of our beautiful planet's stable orbit.
Have you ever really stopped to think about why the seasons change? Or why the sun's path across our sky isn't the same every day? Well, the answers to those big questions are written in the sky, in the sun's predictable annual journey. In this explainer, we're going to dive deep into that journey. We'll be looking at its celestial coordinates and uncovering how this grand cosmic dance dictates everything from the length of our days to the rhythm of the seasons. So here's our plan of attack. First, we need to establish our frame of reference, the celestial coordinate system. Then we'll trace the sun's path through the year, stopping at 4 critical milestones. After that, we'll analyze how the rate of its motion changes, what that all looks like from our perspective here on Earth, and finally, we'll uncover the single fundamental reason behind the entire cycle.
Okay, first things first. Before we can track the sun's motion, we need a map. And for astronomers, that map is the equatorial coordinate system. I want you to imagine a gigantic grid projected onto the night sky, allowing us to pinpoint the exact location of any celestial object. That's what we're working with. Our first coordinate on this grid is right ascension. It's the celestial equivalent of longitude on Earth. Just as longitude measures your east-west position, right ascension measures how far east an object is along the celestial equator. And it starts from a very specific 0 point, a location called the Vernal Equinox, which we'll talk about in just a moment. And our second coordinate, that's declination. You can think of it as celestial latitude. It tells us how far north or south an object is from that celestial equator. If the declination is positive, the object is in the northern celestial hemisphere. If it's negative, it's in the southern. It's that straightforward. Now, here is where things get really interesting. The sun, as it turns out, does not travel along the celestial equator. It follows its own distinct path called the ecliptic. And the most crucial part of this entire discussion is that these two paths, the equator and the ecliptic, are not parallel. The ecliptic is tilted at an angle of 23 degrees and 26 minutes relative to the celestial equator. I want you to burn that number into your memory. It is the key to everything. So, because the sun follows this tilted path, the ecliptic, its celestial coordinates, its right ascension and declination, are in a constant state of flux throughout the year. Let's trace that year-long journey and see exactly how those coordinates change. This right here is the entire annual cycle in a nutshell. You can see the sun moves through 4 cardinal points: the vernal equinox, the summer solstice, the autumnal equinox, and the winter solstice. Each one of these marks a major turning point in the year, and as you can see, each has a very specific set of coordinates. All right, now it's time to zoom in. We're going to dissect each of these 4 key points. What exactly is happening, astronomically speaking, at the equinoxes and the solstices? We begin our journey around March 20th at the vernal equinox. This is the precise moment when the sun, on its ecliptic path, crosses the celestial equator, moving from the southern celestial hemisphere into the northern one. This intersection is so fundamental that we define it as the 0 point for our entire celestial coordinate system. At this instant, the coordinates are as simple as they get: 0 hours right ascension and 0 degrees declination. Because the sun's declination is 0, it's positioned directly over Earth's equator. This means for every observer on the planet, the sun traces a path that gives us an equinox, nearly equal day and equal night, and it rises due east. Okay, let's jump forward 3 months to around June 21st. The sun has now traveled a quarter of the way along the ecliptic and has reached its maximum northern excursion from the celestial equator. This point is the summer solstice. You can see its right ascension has increased to 6 hours, and its declination has hit that maximum value we talked about, positive 23 degrees and 26 minutes. For us in the northern hemisphere, this high declination means the sun appears high in the sky. It traces a long arc, giving us the longest day of the year and causing it to rise far to the northeast. Fast forward another 3 months to about September 23rd. The sun is once again at an intersection point with the celestial equator. This is the autumnal equinox, but this time it's crossing from north to south on its way into the southern celestial hemisphere. Now, the right ascension is 12 hours, halfway around the sky, and the declination is back to 0. And just like the vernal equinox, a declination of 0 means day and night are again of equal length, and the sun rises due east. The observable effects are the same, but the crucial difference is the sun's direction of travel. Finally, we complete our tour on December 22nd. The sun has reached its southernmost point in the sky, its maximum southern declination. This is the winter solstice, the final of the 4 great turning points of the year. At this point, the right ascension is 18 hours, and the declination hits its minimum value, -23 degrees and 26 minutes. In the northern hemisphere, this means the sun traces a very low, short path across the sky, which gives us the shortest day of the year and a sunrise in the southeast.
So we've seen where the sun is at these 4 key moments, but there's a more subtle aspect to this motion. The rate at which these coordinates change is not uniform. The sun doesn't move across our celestial grid at a constant speed.
So let's just pose the question directly. Does the sun's position change by the same amount day after day? Well, if you think about the geometry of these intersecting circles, the answer has to be a definitive no. And here's why. Near the equinoxes, the ecliptic cuts across the celestial equator at its steepest possible angle. This means the sun's north-south motion, its daily change in declination, is at its absolute maximum. Conversely, near the solstices, the sun's path is running almost parallel to the equator. Its north-south position barely budges day to day, so its change in declination is minimal, while its eastward motion, the change in right ascension, is maximal. Okay, we've spent a lot of time talking about abstract coordinates like declination, but what does all of this actually look like to us, standing here on the surface of the Earth? How does this changing celestial latitude translate into what we see with our own eyes every single day? The connection is actually very direct and very simple. When the declination is 0 at the equinoxes, the sun rises due east and sets due west. When the declination is positive, like at the summer solstice, the sun rises in the northeast and traces a high, long path across the sky. And when the declination is negative at the winter solstice, it rises in the southeast and follows a low, short path.
We've followed the sun's path, we've analyzed its changing speed, we've seen the effects on Earth. Now we arrive at the final, most important question. Why? What is the fundamental physical mechanism that drives this entire magnificent cycle?
The entire story, everything we've discussed, comes back to this one number, 23 degrees and 26 minutes. This isn't just some arbitrary angle between 2 imaginary circles in the sky. This is a physical characteristic of our own planet. It is the tilt of Earth's rotational axis.
And that's it. This axial tilt is the prime mover. It is the sole reason that the ecliptic, our view of the sun's path, is inclined to the celestial equator. That tilt is what causes the sun's declination to change throughout our orbit, and that changing declination is what drives the changing length of days, and ultimately, the seasons themselves. It all starts with the tilt.
So I'll leave you with a final thought experiment. Now that you understand the mechanism, consider the consequences. What would our seasons be like if Earth's tilt were far greater, say 50 degrees? Or what if it were nearly 0? The concepts we've covered today give you all the tools you need to work through those fascinating possibilities.
Thank you, friends. Strive for understanding and become wiser. See you soon.